Good evening, all of you. My name is Anil Yadav, and this is the sixth tutorial of fundamentals of micro and nano fabrication. So, most of the slides are taken from the Professor Shushavan's lectures from IISc Bangalore. So today we will see the another additive processing atomic layer deposition. This we have covered in the previous session as well. So we will briefly touch on the atomic layer deposition, and then we will go on physical vapor deposition. So in atomic layer deposition, as the name suggests, there is a deposition. The deposition of the thin film is layer by layer. Let us say this is the substrate, whatever be the substrate. This can be silicon or glass, quartz, anything, sapphire, anything. So if we are depositing any material over that can be Al2O3. Most of the time it is dielectrics, kind of oxides only. So in this one, if you would like to deposit like Al2O3, titanium dioxide, TiO2, SnO2, kind of these kind of oxides can be deposited through atomic layer deposition. As this name suggests, there is the deposition of this thin film over the substrate. This is substrate, and this is the film, whatever, like Al2O3. This happens layer by layer deposition. Okay, the mechanism and the process we will see in the subsequent slides. So this is also atomic layer epitaxy. Atomic layer epitaxy is it is following the same kind of crystal structure as that of the bottom substrate, or we can say the crystalline deposition. Crystallinity of the film will be very good. Okay, so this is a layer by layer growth. The growth of the film is a bit slow, because there is a layer by layer growth, slower than that of the chemical vapor deposition that we have seen previously. So that will be slower then, but the quality of the film will be very good. That will be the more crystalline, and we can change we can play with the parameters accordingly to get what type of films do we want. Okay, and the best part of this is at low deposition temperatures, like 150 to 300 degrees Celsius. We can deposit aluminum dioxide or zinc oxide, tin oxide, titanium dioxide. These kind of films can be deposited at very low temperatures. So for the lower temperatures, we can have a selection of a wide variety of substrates. You can take ITO, you can take maybe for lower temperatures you can take plastic as a substrate. For the flexible electronics, you can do deposition over the flexible substrates. You can deposit oxides, metal, nitrides. Nitrides are a bit difficult to do because of the precursors. So for nitrides, for oxides, there are precursors like okay, in the next slide we will see how that comes. So the atomic layer deposition, that you can see, this is a trench. There was a trench in the silicon. Okay, so if you want to do a very conformal kind of growth, then atomic layer deposition is the best thing. Okay, so this is highly conformal. The ratio, these trenches are very deep, and that you can see the white layer, which is the zinc oxide over the silicon, that is completely following the trench. Okay, and this roughness is in the substrate itself, and it is following that roughness as well. So the RMS roughness you will get is less than 1 nanometer, which is very highly kind of a good kind of thin film. Okay, so in atomic layer deposition, what happens is in atomic layer deposition, so there is a precursor. Okay, precursor of the material that we would like to deposit. That precursor can be of mostly these are organometallic precursors. that is the name suggests organic and metal, which is kind of a there is a organometallic precursor, and that can be there can be chloride precursors as well. So these metal organic precursors, just wait a minute, let me check. Okay. Okay. So in ALD, what happens is there are two precursors. One is the organometallic precursor, or organometallic or chloride. That can be chloride precursor as well. It's like zinc chloride, molybdenum chloride, and these kind of precursors can be there. And second one is the oxidant. For the metal oxides. For the deposition of metal oxides, one will be the metal containing precursor, another one will be the oxidant. So that can oxidize the previous precursor over the substrate to deposit the desired film. Okay, so let us say there is a precursor A and precursor B. One is the organometallic and another B is the oxidant. That can be oxygen, ozone, or H2O. These kind of gases can be there for the oxidation of the previous precursor over the substrate. So what happens is this is a one ALD cycle. So this complete whole sequence is the one ALD cycles. Initially we give me. Okay, so there is a chamber. Okay, there is a chamber. So there are some lines which are connecting the precursor A, precursor B, and one is the nitrogen for the purging. Let us say this thing. Okay, so there is our substrate inside the chamber, and one is the outlet which is connected with the vacuum pump. So initially what we will do is we will give a dose of the precursor A. This precursor A will be chemi-adsorbed over the substrate. Okay, this adsorption is chemi-adsorbed, which is this precursor is forming a chemical bond with the there are some OH. This let us say this is silicon or glass or anything. So these are OH terminated, already OH terminated surfaces, or if not, you can make it hydrophobic or hydrophilic by some treatments. Okay, so after that, as soon as you give a dose of the precursor A, that precursor will be chemi-adsorbed over the substrate, and this adsorption will be kind of a self-limiting in the sense there won't be any reaction between the A and A. Let us say this is the substrate, this A won't react with the A, so there one end of the A precursor will react with the substrate, and that will there will be a single monolayer of that this precursor will be there over that, and this is chemically active for the second precursor. Then we will purge the system in the sense with the nitrogen. We flush the system with the nitrogen, so that if there is any extra adsorbed A material is there, not extra adsorbed, if there is any material left in the chamber, so that we can remove that extra material from the chamber outside. So we will flush it with the nitrogen, and we will turn on the vacuum pump, so that it extra material of the extra A precursor will be removed. Otherwise what will happen is, as soon as we give the B precursor, that will react in the air itself. Okay, so then we will give the dose of the precursor B. That precursor B is chemically active towards the precursor A. Okay, so the other end of the precursor A will be chemically active with the B, so there will be a deposition, and there will be a reaction in between the A and B. So the another layer of the B will be forming over precursor A. Okay, So in this process, this is the kind of reaction which is a self-limiting reaction is there, A plus B is there. So whatever extra is left over here, then again we will purge the nitrogen, and it finally we will get this kind of the monolayer. This is the monolayer of the material that we got. That can be if you are depositing zinc oxide, then can be zinc oxide, aluminum dioxide, silicon dioxide, molybdenum oxide, any kind of the whatever you would like to deposit. Most of the these ALD systems are mostly used for the oxide depositions, and where you need a highly conformal coating of the material if you need, so then you can use the ALD. So this till here it completes the ALD cycle. Again we will pulse, we will give a dose of the A, and that will cover the layer again, and this is where we started from the first step to this sixth step. This sixth step will come again as the first step. Okay, it is terminated with the A. Okay, this is the kind of reaction that happens in the ALD. This is the one cycle. So one cycle typically forms around 0.1 nanometer of the thin film. 0.1 nanometer of the because this is a kind of monolayer now. So almost if you are depositing here Al2O3, in Al2O3 if you are using TMA and ozone or H2O, so it generally forms 0.11 or 0.12 nanometer of the of film in one single cycle, and a single cycle typically takes around 1 to 2 seconds. Around 2 seconds it takes, because there is a purging step as well. So in 2 seconds you are depositing 0. So that's why it is a bit slower process than as compared to the CVD, because in CVD what we do is instead of alternating cycles of A and B, this is a chamber. So we what we do is we simultaneously give A and B. Okay, we simultaneously give the doses of A and B. So here is the substrate, and the substrate is already heated so that those kind of reactions happens at very high temperature. So wherever there is a high temperature, so these kind of reaction will take place at that surface. Okay, that can be a wall heating also, that can be substrate heating as well. So if you are heating only the substrate, so there will be a reaction over the substrate only. So that typically happens at 500, 600, 700 degrees or more than 1000 of degrees it happens. So but in ALD typically happens at in between 150 to 300 degrees Celsius. Okay, it is very at lower temperatures you can do the deposition. Okay, so just so in this, and next one is so what kind of materials and precursors that you can use. So in ALD the precursors are usually metal organics, metal organic, or you can say some metal chlorides also you can use, and that all those should be volatile, so that there should be a partial pressure in the bubbler as well. Bubbler, I can show you. There is something, bubbler is there is a kind of mug type of thing you can say. So this is a bubbler. So here there is a nitrogen inlet and there is outlet. So you fill this bubbler with the precursor, and you can bubble the nitrogen through it, and what this nitrogen will take is it will take the vapors of the precursor, and this will go to the chamber. Okay, this will go to this nitrogen, you can say nitrogen is the carrier gas here. This nitrogen will carry carry the vapors of the precursor, that can be metal organic or the metal chloride as well. Metal chlorides are kind of dangerous, so they are typically less used because of the health hazards and environmental hazards. Mostly metal organics are used, but these metal organic precursors are also pyrophoric. Most of them are pyrophoric, and so that is why care must be taken while doing the atomic layer deposition. Okay, so and another for oxides, what you can use is H2O, O2, O3. These are the oxidants. That is the second precursor which I was telling. One is A and another one is B. The second precursor B is the oxidant, which can be H2O, O2 or O3. And for nitrogen, for nitrides, you can use some for oxides only, you can use the plasma with nitrogen or carbon dioxide as well. And for nitrides are like you can use N2, that is very high temperatures, let us say 1000 degrees Celsius, because N2 is highly stable and it doesn't decompose. Okay, but the another precursor that you can use is NH3. Okay, it is stable, but at higher temperatures you can deposit nitrides, and H2S for sulfides, PH3 for phosphides, these kind of precursors that you can use. And mostly for aluminium deposition, this trimethyl aluminium is used, and for zinc oxide, this diethyl zinc is used. These two precursors are highly pyrophoric, and we can say the volatile materials. Volatile, why do you need the volatile material is because they should react at lower temperatures, or they volatile, maybe you can say there should be enough partial pressure in the bubbler itself, so that you should not there is no need of the nitrogen as the carrier gas. And there are some ALD chambers, so what they do is they just use only a single they do not bubble the nitrogen through it, so they do not use even the nitrogen as a carrier gas. They just open this wall to the chamber, so there is enough partial pressure inside this bubbler that can give a small dose of the material inside the chamber. Okay, so that is why the volatility of the precursor is important. And another thing, this should be a kind of highly reactive with the substrate. Okay, so that to make the reaction as fast as possible, so that it can take less time for the deposition. Okay, so these are the mostly used diethyl zinc and trimethyl aluminium. Mostly aluminium dioxide is deposited through this ALD, atomic layer deposition method, for kind of isolation, because isolation is required in solar cells, LEDs, in these kind of devices. Isolation is required. In that case, a highly conformal growth is needed. So in that case, this ALD can be used. And okay, this is the Al2O3 deposition using the trimethyl aluminium. So how does it? So as initially I told you that the substrate is initially kind of OH terminated. If it is not, you can make it hydrophilic by plasma treatment or by UV ozone treatment, and or another maybe you can just through the plasma treatment as well you can do. And otherwise you can pulse the H2O or oxygen initially in the chamber. Okay, that is precursor A, B. You can pulse the maybe 10 pulses of the H2O you can give, so that to make it more hydrophilic. Okay, so it will increase the reactivity of the substrate towards the trimethyl aluminium. If you are not getting a good kind of film which is not uniform, a kind of non-uniform or kind of islands you are it is forming, then you can check the if this method can work or not, because that might be that could happen because of the TMA is not that much reactive with your substrate. And as soon as you give the dose of the precursor of trimethyl aluminum, that this aluminum will react with the there are kind of if you would like to go in the mechanism, so in oxygen there are the lone pairs that can act as a Lewis base, okay, and in this one aluminum there are vacant orbitals that can act as a Lewis acid, so there will be a Lewis acid base reaction in between this OH and this precursor. So according to through that reaction, Lewis acid base reaction, this will form a chemical bond with this one, and there will be a release of the methane, okay. And so this is a kind of reaction that happens, and subsequently you can give the dose of the H2O, which is the precursor B. With this dose it will oxidize this surface with it will again react with the same Lewis acid base reaction, and it will again remove the methane, okay. So finally you will get a OH terminated again after this is the one cycle, this is complete one cycle, and finally you will be getting a OH terminated surface, and again if you will give if you will dose it with the trimethyl aluminum, this trimethyl aluminum will react with this one, and this cycle continues. So okay, in this one, so there is a layer by layer growth, okay. It's layer by layer growth in the sense that first this trimethyl aluminum will react with the substrate, and then that oxidant will react, that completes the one cycle, and this completes the one monolayer of that material or the substrate, okay. So this is the mass gain over the substrate. How does it happen? So okay, if there is a the dose is sufficient or not, and so that purge time is sufficient or not, so you need to take care of these two parameters. One is the dose time and another is the purge time. So by controlling these two parameters, you can just optimize the reaction, optimize the ALD process, okay. And another one more parameter is the temperature. The substrate temperature also plays a critical role whether the reaction is happening or not. There are two things, one is the reaction over the substrate, and another one is that if the dose is sufficient or not, okay. So there should be a reaction also over the substrate. So if this TMA is highly reactive, as soon as you dose the TMA in the chamber, so this TMA will react as soon as it sees the oxygen hydrogen bond, oxygen is there, as Lewis acid is there, so Lewis base is there, so that it will react with, and there will be a formation of the chemical bond. So in between this, so as soon as after this TMA dose, you need to purge the system with nitrogen, okay. So this, if you won't purge the nitrogen, then there will be a reaction in between TMA and H2O in the chamber, which is in the air, okay, if there is a residual of TMA in the chamber, okay. So let us see this how this process, how the mass gain, how this you can get this graph is, there is a kind of crystal monitor, okay. Instead of putting your substrate over that, you can put your crystal monitor inside the chamber, and you can with the frequency it checks the how much mass gain is over there on the substrate. So with the thickness, sometimes if you need to check the thickness, you can check the thickness with the crystal monitor. And now we are checking with the mass gain, how much mass is gaining with the each cycle of the TMA or and H2O, okay. With each ALD cycle, how it is gaining the mass. So can you see, this is the dose of the TMA, This is the dose of TMA. Initially, this as soon as you give the dose, the mass of the mass gain on the substrate or crystal monitor will increase. Okay, then it will get stabilized. The mass will get stabilized. Okay, so this is the point. Till this point, if this is the TMA dose, till this point you can dose the TMA. Okay, if you are dosing the TMA till this point, or let us say till this point, so you are you are just wasting time, and you are also wasting the your precursor. These precursor are highly expensive. Okay, so you should not you should not waste this precursor as well. And so in this case, what will happen is, so if you are dosing till here, so there is no use, because it is not gaining the mass. Till here, the it has already formed the monolayer over the substrate. Okay, as this reaction is self-limiting, so however how much TMA you will give, so that won't be adsorbed or chemically adsorbed over the substrate. Okay, so it will just go out through the exhaust. So till this point, as it starts saturating, till that point you can dose the TMA, and then you need to purge the TMA. So then the nitrogen, so you will pass the nitrogen, you will flush the chamber with the nitrogen, so that if there is TMA inside the chamber, actually there will be, so that should get removed. Okay, so you will purge the system till the point when whole this TMA should be removed. Okay, you will purge this with the nitrogen. And another case is, if you are dosing the TMA, but your dose time is very less. Let us say at this point you are till this point. Okay, so your dose time is very less, so you are dosing the TMA with the very less amount. So what will happen is, so there will be a partial reaction will happen. So you will there won't be any uniform growth. You will find some island kind of growth will be there, or at some point there will be more growth, and at some point there will be less growth. You will be encountering these kind of problems. Okay, let us see. I think someone wants to join this. Okay. So this kind of reaction will happen. So if you dose it with then there will be oxidation. If you how will you oxidize it? With the H2O dose you will oxidize, then again you will purge the system. So H2O will chemi-adsorbed over the substrate it will react with the TMA, the previously active TMA, and then again you need to purge it with the nitrogen. Okay, so this is the single this till here it is the one cycle of the ALD. Okay. So ALD growth, so ALD proceeds with a series of self-limiting growth steps. As we alternatively give the doses of the precursor A and B, and with the after giving several number of cycles, you will find there is find that some material has deposited, and then you will check the growth per cycle, often called the GPC. Okay, growth per cycle, you will check how with the per cycle how much growth is happening over the substrate. Okay, and this growth is linearly increasing with the number of cycles. So with the self-limiting nature of the chemisorption, so this let us say this is a diethyl zinc. So as we have seen, this is a growth rate, or you can say that is the mass gain. Okay, mass gain with the dose time. Okay, this as you are, this is the dose time, as you give the dose, and it the mass gained by the crystal monitor will be increasing. And after this point it is constant, it is kind of constant. Okay, so after this point you can this till this point, if you are giving the dose before, if you are your dose time is less, okay, there will be incomplete chemisorption, and after this point there will be a complete chemisorption. You will get a very good kind of growth, highly conformal and a uniform growth will be there. Okay, so, and another thing is this growth rate is kind of independent of the pressure. So unlike chemical vapor deposition, in chemical vapor deposition, that is highly dependent on the on pressure. Okay, but in this case it is not that much dependent on the pressure. So uh, this is a plus point for the atomic layer deposition. Okay. Last time we have covered most of these things, so if you have any doubt you can ask me, otherwise we will just go through these points. Okay, so last time we have, you can watch the video if you have any doubts. So okay, so this is the effect of the of of if your dose time is lesser than this point, then this is a suboptimal growth. Okay, suboptimal dose. And in this one, so there will be, this is the inlet this side and this is the outlet. So most of the precursor is in this region initially, so it will react as soon as it enters the chamber. So it will react this side of the wafer. Okay, so in this region of the substrate there will be very less growth. Okay, so because of that, this is the, because of the suboptimal dose, there will be a non-uniformity in the deposition because of the insufficient dose. So you need to increase the dose time, or you may need to increase the partial pressure of the dose of the precursor. Okay. So let us wait for if someone is there, because last time we have covered. So let us go let us go to the okay, another method for the deposition, another additive processing is the physical vapor deposition. In physical vapor deposition, what happens, we physically heat the material. In physical vapor deposition, you already have a material like zinc oxide. If you want to deposit, you will be having a target of the zinc oxide. If you are depositing any metals like platinum, gold, silver, calcium, this kind of materials, if you would like to deposit, you will be having that material, and you physically either heat the substrate, sublime, whatever you do, so kind of thing, and that sticks physically with the substrate. Okay, you heat, make it, evaporate it, and that evaporate through the evaporation that heats up. It is the same process like if there you are heating the you are boiling the water, and there is a lid over that, over your pressure cooker, or over the or the container. So that due to the evaporation, the water gets stick over that lid. Okay, so this is kind of the same process. So PVD, in PVD, this is the we can say physically you heat the source, and then evaporate, these vapors get stick over the substrate. So this is physically transported to the substrate, and the method of generating the vapors are different. Okay, so you can evaporate it, you can sputter it, and based on that there are different names: sputtering, e-beam evaporation, how you are evaporating the material. So based on that there are different type of systems like thermal evaporation, physical and another pulse layer deposition. These kind of processes are there. So in this one we will be covering this thermal evaporation. Okay, so mostly metals are deposited for this, for the connecting electrodes. These metals are deposited through the thermal evaporation kind of technique. So what you do is you take the gold or silver in a crucible. This is the crucible. In the crucible you take the gold and you pass a very high current through the crucible, and that crucible gets heat up, and this the boiling temperature of the crucible is much lesser than that of the material which is inside the crucible. So that the material gets evaporated and gets deposited over the substrate. Okay, so and PVD often done at very high vacuum, which is less than 10 raised to power minus 3 torr. Okay, it is that we will see why it is done at very high vacuum conditions. Okay, and so what sort of vacuum is there? So there are, and what sort of processes can be done at the different vacuums? So 1 atmosphere is kind of 760 millimeter of Hg. That is the high school, in high school physics you must have read this thing. 76 centimeter of the mercury level goes. Okay, and which is equal to 760 torr, which is 10 raised to power 5 Pascal and 1000 millibar. Okay, 1 atmosphere is equal to the 1 bar of the pressure. So this is the 1000 millibar, and in between 1000 millibar to 1 millibar, that is the low vacuum. And in this kind of vacuum you can do atomic layer deposition very easily. Okay, so and below that 1 millibar to 10 raised to power minus 3 millibar, this is the medium vacuum. So kind of roughing pump can be used, and this pressure can be reached within several minutes. Okay, and this is the in between 10 raised to power minus 3 millibar to 10 raised to power minus 6 millibar. This is the high vacuum, and this is the region where evaporation or this e-beam evaporation kind of, or thermal evaporation is done. In this region is mainly sputtering is done. Initially for sputtering as well we go to the high vacuum, and then we go for the argon, because argon, we generate the argon plasma, so that we come back to the pressure in this regime after passing the argon. Okay, and this is the very high vacuum. Generally SAM is done because in that there is you use electron kind of electron gun, so that should be kept at very high vacuums. This is ultra high vacuum and extreme ultra high vacuum, so these are of no need. There are several pumps that can be used for these pressure ranges. Okay, rotary pump, mechanical pump, or this oil pump can be used till this pressure, but okay, and so you can just go through the pumps. So these kind of pumps can be used for several applications for to get the different vacuums. So if you go very high vacuum in these vacuum regimes, so the expensive the prices of these pumps goes up. Okay, and okay, So let us see the mean free path, because it will be it will be required for the for how you are depositing the material. That should not get that should not be uh, uh, like that should not collide with the impurities. Okay, so if there are some impurities, some gases are there inside, if that is not very high vacuum, okay, let us say if your chamber is not high vacuum, so transportation of the material from the crucible to the substrate will be very difficult, because there is the material that you are evaporating, that will collide with the impurities or with the oxygen, nitrogen or whatever, and will deviate from its path. Okay, and also it will form oxides, nitrites, sulfides. These kind of impurities will get deposited on your substrate, but that will hamper your device. Okay, so mean free path is the distance, average distance traversed or traveled by that molecule in between two successive collisions. Okay, so this is the lambda, which is given by this formula. So this is the mean free path. So at higher pressures, the mean free path is less. At higher vacuums or lower pressures, so the mean free path increases. Okay, so this is the pressure in millimeters, and this is the mean free path in centimeters. So as you decrease the pressure, the mean free path increases. Okay, and the impingement rate is number of particles passing through an area. Okay, this is in a hypothetical area, the number of particles per unit area per unit time passing. Okay, that is the impingement rate, which is GA, and given by this formula. Okay, and monolayer time is the time required to deposit a monolayer form of that on a clean surface. Okay, so this is the monolayer time, and let us assume whatever going through this is also depositing over the surface. Okay, whatever is coming in contact with the surface is depositing. Okay, so and now what we can see is the pressure. This is the pressure, this is the time taken for the monolayer to get deposited over the substrate. Okay, this is the 1000 millibar. 1000 millibar is the pressure. So at that pressure, how much time does it takes, whatever. Okay, so at 1000 millibar, and so whatever is in the air, whatever are the molecules, they all will get stick. Let us assume that they all will get stick. So it will just take 10 nanoseconds to get deposited a monolayer of that layer thickness. Okay, this is where atmospheric chemical vapor deposition works. So that is why the growth rate or the deposition rate of the atmospheric CVD is very high. Okay, and if the pressure is 1 millibar, so that is the low vacuum regime. So this is the low vacuum regime. So this is the impingement rate. Impingement rate decreases with the pressure as the pressure decreases, because there are very less number of molecules. Okay, and this tau, which is the monolayer time, that will increase. Okay, so we should work in that regime where there will be very less kind of impurities, and there will be high deposition rate as well. Okay, so in 10 raised to power minus 6 millibars, so this will be the impingement rate, and this will be the mean free path, and 10 seconds, it will take 10 seconds to form a monolayer. This is where the evaporation does evaporation uh, technique works. Okay, so that we have already seen. So in CVD we work with that there was a number, I forgot that. Here we work with the Knudsen number. So lambda by d, it is given by the lambda by d. Okay, with d is the tube diameter. Okay, d is the tube diameter and lambda is the mean free path. So there are some regimes which is a molecular regime and viscous regime. So in this evaporation techniques typically works in the molecular regime. So now a physical vapor deposition. In physical there are some other techniques, some evaporation, sputtering, pulse laser deposition, and e-beam evaporation. So today we will see the evaporation technique. So that can be thermal evaporation or e-beam evaporation. Okay, let us see first the thermal evaporation first. So in thermal evaporation, what is the idea is, so this is the a hot filament. This filament that can be made of the very high boiling point material. So and here we put the crucible. So that crucible can be also be made up of very high boiling point material, and in that crucible we put our material. As we heat the crucible by passing the current through this, so that will evaporate. That material will get evaporated and it will get deposited over the substrate. Okay, so this is the idea. And so the procedure here converts the metal from the solid to the vapor phase, okay, by evaporation, and transport gaseous metal to the substrate. So by evacuating it to the very high to high vacuum regime, which is around 10 raised to power minus 6 millibar. Okay, in this regime as we go, so there will be a very high this what to say, okay, what it was, mean free path. Okay, sorry. So the mean free path will be very high, so it will get deposited over the substrate. Okay. So in evaporation we need very high vacuum, that as I told you, if there will be very a more number of molecules of gases, so this mean free path will be lesser and it will get collided and it won't reach to the substrate. Okay, and also there will be very highly non-uniform growth. So as this will get evaporated, it will collide with these molecules and it will be also depositing on the walls too much. Okay, so this is the idea. And at low vacuums it is reaching, the deposition rate is a bit high, but still it is not that much faster than as it will get in the high vacuums. Okay, and as we decrease the film purity will be increasing. Okay, the base, as we increase the base pressure, as we decrease the base pressure, the film will be more pure than that of the other materials. Okay, let me check whether no one is there. So okay, this is the evaporation. Okay, I think, okay, this is the electron beam evaporation technique. So in this one what we do is we heat the it with the by passing through the the, by passing a current through the filament. So in this one, the crucible is also heating, but in this one, this is the electron beam e-beam evaporation technique. So what we can do is, so we there is an electron beam source, so that uh, this electron beam is made to fall over the material, and this create a very local heating over of the material, and it will get evaporated. Okay, it will create the local heating and it will evaporate the material, and this material will get deposited over the substrate. This is the thing. And there are some crucibles and materials. Okay, so I think let us stop here. So next time we can start the another deposition technique, which is the, okay, someone would like to join them this. Okay, I think huh. Okay. Okay. So in evaporation, you need a very high vacuum because of because of the region. If there won't be very high vacuum, this the material that you are evaporating will get will be these are the okay, the molecules of the in the atmosphere, so it will get collided with the it will collide with the atmosphere, and there won't be that much deposition over the substrate where we want it. Okay, so in lower vacuums there will be less collision, and the mean free path of the material that we would like to deposit will be higher, and in this case the mean free path will be lesser. Okay, so there will be less deposition over the substrate because it is typically around the this length is around 30 centimeters. Okay, 30 centimeters, but at lower vacuums or at higher pressures, so the mean free path is very less, so it won't reach to the substrate, and at higher vacuums it will the mean free path of the material that we are depositing will be more. Okay, in that case it will deposit over the substrate. But in another there will be scattering, and there will be some impurities as well, because if there is oxygen, nitrogen, sulfur is there, so that will form oxides, nitrides or sulfides, as some, if you are depositing gold, calcium. In calcium is highly reactive. Okay, so the work function of the calcium is very less, and it is desired for some LED applications. So if you are depositing calcium, so that calcium will form calcium oxide. Okay, this calcium oxide is will be is harm to your device, because this calcium oxide is non-conductive, and you are depositing calcium for the as a metal for connection. Okay, and in another case, okay, now the evaporation. So how the background pressure that we are using sophisticated pumps kind of, so to reach to the higher pressure, to lower pressures, or we can say at higher vacuums. Okay, so as you decrease the pressure, as we are decreasing 1 millibar, 10 raised to power minus 3 millibar, 10 raised to power minus 6 millibar. In 10 raised to power minus 6 millibar, typically we do the evaporation. Okay, we typically do the evaporation deposition. Okay, in that range, this is the monolayer deposition time, which is okay, or no, this is the impingement rate. Okay, the impingement rate is 10 raised to power minus 1. As you decrease the pressure, the impingement rate will also decrease, because there will be very less number of molecules because of the lower pressure. Okay, but the material, the impingement rate is irrespective of the material we are depositing. It is with respect to the pressure. Okay, that can be other molecules as well. The atmosphere, oxygen, nitrogen, can be anything. Okay, that this impingement rate is that case. Okay, the time to deposit a monolayer will be 10 seconds in this case, where we are doing the evaporation. Okay, so now if we the another thing is the melt pressure, and we need the impingement rate, or the we can say okay, this is the melt pressure, or we can say the partial pressure of the melt that we are depositing. Okay, we are evaporating our material, and that melt pressure is this one, 10 raised to power minus 4 millibar. Okay, this, and the pressure or this is the base pressure. Base pressure is the pressure of the chamber, and that is the total pressure. Okay, that is the total pressure including this melt pressure. Okay, if this, the base pressure is 10 raised to power minus 3 and the melt pressure is 10 raised to power minus 4, the arrival ratio is nothing but okay, this is your substrate, and there are oxygen, nitrogen, or any material is also there, and this is your crucible, and you are evaporating. Okay, your melt pressure is this 10 raised to power minus 4 millibar, and the arrival ratio, how many molecules of your material, okay, how many molecules of your material are reaching to the substrate, and to the ratio of the how many material molecules of your this material is reaching to the atoms in the atmosphere. So there are some oxygen is also reaching, nitrogen is also reaching, there are other gases also, gaseous molecules also. Okay, so this is 10 raised to power minus 1. So if your melt pressure is 10 raised to power minus 3, so that means this 10 raised to power minus 1 is the arrival ratio. That means your one molecule of your material is reaching the substrate, and 10 molecules of the other material is also reaching. So the arrival ratio is very poor. So okay, so if your base pressure is lesser, so 10 raised to power minus 4, so this is, and your melt pressure is 10 raised to power minus 4 also. So in this case, so how much your molecules are reaching is 1:1. Okay, one molecule of your melt is reaching, one material is reaching, and one molecule of other gas is also reaching over there. Okay, so this arrival ratio defines how much pure you can create, you can deposit, how much pure material you can deposit. Okay, this, if we are increasing, if we are increasing the base pressure, okay, I mean decreasing the base pressure and increasing the vacuum, okay, vacuum level, so the arrival ratio is improving. So that means you are making more and more pure of the film. Okay, that can be silicon dioxide, sometimes aluminum dioxide is also hafnium oxide. So these kind of films are also deposited through the e-beam, either e-beam evaporation, either thermal evaporation, sputtering. These kind of techniques are used for the deposition of these kind of the films. So lower the base pressure, much better the quality of your thin film will be. Okay. Okay, so now this is the evaporation equipment. So here there is a crucible, in crucible, let us say there is gold or something is there, and this is the shutter. So whenever you are not depositing but you are evaporating, your temperature is increasing, you will check the with the crystal monitor, your deposition rate gets constant or not. Then you, till then this shutter will be there, and then you will remove the shutter, and this is the vacuum pump to create the higher vacuums. Okay, and okay, so this is the impingement rate of the material. So you are depositing the material, and what is the impingement rate of the material you are depositing, that will define us the deposition rate of the material. Okay, so that depends on the pressure of vapor pressure of the melt. Okay, that vapor pressure of the melt and the base pressure, how much vacuum you are creating. Okay. Okay, so these are the temperatures. This is the temperature and this is the vapor pressure of the material. Okay, so this is the vapor pressure. If you are heating any material, so this is the vapor pressure of the material with the temperature, that will depend. Okay, this is the vapor pressure versus temperature curve. So molybdenum, and this is the molybdenum, and this is the tungsten. So the vapor pressure of the tungsten is very less even at very high temperature. So these materials are generally used for crucibles. Okay, so if you are depositing any material in this range of the vapor pressure, so at, let us say, at 1000 degrees Celsius, so at 1000 degrees Celsius, the vapor pressure of molybdenum will be very less, and the arrival ratio for the aluminum versus the molybdenum will be very high. Okay, will be very high in the sense aluminum will be, content of the aluminum in the film will be very high than that of the molybdenum or the tungsten. Okay, so this is the thing. Okay, so no one is there in the meeting. Okay, this is the kind of board. This is a dimple board, you can say. There is a dimple kind of thing in the board. So you just put your material in that and put this like this. You pass a very high current over through this one, which will heat up this board, and there will be whatever the material is there, that will be evaporated. Okay, so this is a crucible. This crucible is surrounded by a resistive wire, this kind of resistive wire, and we pass the current through this one, that will heat up the material, heat up the crucible and the material, and it will the material will get evaporated, and it will get deposited over the substrate. Okay, most of the metals are deposited through this method. So and okay, let us stop here today. So maybe in the next class we can discuss more about this thing. So in the next class, if you have any doubts, you can ask me. So if you have any doubts in the assignments as well, we can discuss in the assignments as well. Okay, thank you for your time.